Hello folks, welcome back to my basement. I am here today to make a recording for PSQF 6242 Lecture 7, which we did not get to in class, but which I want to have available for other classes. So we are going to be talking about how to test moderation that involves multiple slopes simultaneously. So a long list of topics. We have an example to follow for some of it. Away we go. So just to bring us back to the idea that some predictors in general linear models are going to require more than one slope to describe their effect. So this happens for categorical predictors that have three or more groups, and it also happens for quantitative variables whose effects are described via nonlinear functions, such as quadratic effects or piecewise effects. But focusing for now on how one includes the effects of categorical predictors in the model. I have shown you one type of strategy that I think is most useful for getting started. However, I would be remiss if I didn't show you a different strategy that is actually much easier, and that one would tend to use in practice more often, especially if your categorical predictor has lots of groups. So one alternative that we've discussed this semester on how to create predictors out of your categorical variable is to create dummy-coded group contrasts. And so we would use C-1 contrasts for C possible categories. We would put them all in the model at once, and they would be treated as binary predictors that are essentially quantitative. So they capture the effect of a 1-unit change in each dummy code, moving from the 0 value to the 1 value. The reason that I start here is because this coding scheme maps directly onto the linear model representation of how groups get included as predictors in a model, and also because this is the easiest way to think ahead of time about who you want as your reference group and what kind of group differences you want to directly include as model parameters. Behind the scenes, though, there is another option in which you can let the program do all of that dummy coding for you. And that is known as the program treating your predictor directly as categorical. So it's going to involve a new statement in Sass known as class. It's an I dot instead of C dot in Stata, and it corresponds to the by statement in SPSS syntax, or what is known in Windows version of it as the fixed factors box. The only catch in doing it this way is that it chooses the reference group for you. This is difficult to change on the fly in Sass or SPSS, but it is easy to change in Stata. And this approach sort of hides from you the logic of creating group contrasts, but it can be more convenient if you have many groups. You want a lot of different contrasts out of your groups, different ways of combining groups or looking at differences between group means, or if you have interactions. And it does make it trickier, though, to interpret main effects that are either conditional or marginal in the context of interactions. So we'll start by reviewing this first strategy, which we went over this semester. So for instance, if I had a model in which I wanted to include one four-group categorical predictor. So let's say this is a situation in which I'm comparing differences between a control group, which I want as my reference, and three different types of treatment groups simultaneously. So I might create three new variables, D1, D2, and D3, and these are the values that they would take on for the different groups. So groups across the top here. If it's the control group, they all get a 0. If it's treatment 1, only the first variable picks up a 1. If it's treatment 2, the third variable picks up a 1. And nope, second variable picks up a 1. I'm going the wrong way. And if it's treatment 3, then the last contrast picks up a 1. And so these new variables would go into the model like this. This model, by the way, would be called a one-way analysis of variance. I'm thinking of it as a general linear model, but you may know it under that terminology instead. And even though there are only three group differences included directly in the model, there are actually 6 possible group differences that the model creates indirectly as well. And so the model's job is to recreate the predicted mean for each unique value of this categorical predictor. And the way that it does it is shown in the table here. So beta 0 is always the fixed intercept. It is the expected outcome when your predictors are 0. Given this coding scheme, that corresponds to the predicted outcome for the control group. Beta 1 is going to give us the difference of how the treatment 1 group differs from control based on my coding scheme here. And so to get the treatment 1 mean, we would add the intercept for the control plus how control and treatment differ, which gives us beta 1. So beta 0 plus beta 1 equals the treatment 1 mean. The same thing happens for the two other groups using their respective contrasts. And so given that the model tells us how each group gets its own mean, it also must tell us how the group differences would be computed as well. So here they are. Given the model, here are the group means as created by the model parameters. Here are all 6 possible differences between my 4 groups. So each of the differences involving the reference control group versus each of the treatment alternative groups is given directly by a model parameter. So note the order of the terms here. To figure out how control and treatment 1 differ, if I'm thinking of control as the reference, what I'm asking is how treatment 1 differs from control. So treatment 1 is listed first, minus control as the reference group. And so given that treatment 1's mean is beta 0 plus beta 1 times D1, which takes on a value of 1, and the control group's mean is given just by beta 0, if I do the math here, the beta 0 terms drop, and I'm left with beta 1. So beta 1 directly is the answer to this, how treatment 1 differs from control. The other two treatment groups versus control are given in a similar fashion, just swapping out how their means are given to us by the model parameters. The remaining 3 are the differences among the non-reference groups, and those are given by the model just indirectly. So in this case, beta 0 plus beta 2 is how we get the mean for treatment group 2. If we want to compare that to treatment group 1 as the reference, then we put in how the model gives us treatment group 1's mean. If we do the math, we find that the beta 0 terms drop, and we're left with beta 2 minus beta 1 as the answer to how treatment 2 differs from treatment 1. The same pattern happens in comparing each of the other treatment groups to each other. It's always the effect of the alternative group minus the effect of the new reference group. So a linear combination of one slope minus the other will always give you the model implied differences among the non-reference groups. So even though there's only 3 slopes going into the model does produce all 6 possible pairwise or between sets of 2 differences, and it can be used to produce any other differences that are linear combinations. So we could lump together all 3 treatment groups and ask for their mean versus control, and the model would allow us to get that information at the same time. So to do that process in software, here's what it would look like in SAS. So I have my proc GLM. It will become proc mixed in the longitudinal course, but the setup is very much the same. We have a model line where the outcome is just given y in this generic example. I would put in the 3 dummy codes into the model, so it's outcome equals predictors. The slash denotes options, and so this is controlling the alpha level by which to compute confidence limits for all the parameters, as well as effect size estimates, which are available in GLM, unfortunately not in mixed. I have a contrast statement that would lump together all 3 of these dummy codes to get what it would be called an omnibus or overall effective group. In this case, that would be the same as the f-test for the model because all the model contains are these 3 parameters for group differences. And then I could write estimate statements that would give us the model predicted mean for each of the 4 groups. And so they use the equation. I would need 1 beta 0, so the word intercept refers to whatever beta 0 is going to become. D1 refers to whatever the slope beta 1 is going to become. And if it's for the control group, the variable D1 would take a value of 0 as well as the others. So in these statements, the words refer to the betas, to the fixed effects that are going to be estimated by the model. The values refer to the variables that multiply those fixed effects, and it's based on what combination of predictors you're trying to create a model predicted outcome, or group mean in this case. So the pattern of zeros and ones corresponds exactly to how these variables were constructed initially. D1 turns on, has a 1, so to speak, when we're talking about the treatment 1 mean. D2 turns on if we're talking about treatment 2, and D3 turns on if we're talking about treatment 3. The remaining 6 estimate statements then are giving us the pairwise group mean differences. The first 3 are actually redundant with the model, but they're included here for pedagogical purposes. So if we want control versus treatment 1, we need 1 beta 1. We don't need any beta 2s or beta 3s. And so this is just not a linear combination of parameters required to get to this result. It's just beta 1 all by itself, just beta 2 all by itself, and just beta 3 all by itself. The remaining 3 estimate statements provide the differences between the non-reference groups, and these can be understood by looking up here at the estimate statements for how each group got its mean in the first place. So if I want T1 versus T2, I'm treating T1 as the reference, and I want to know how T2 differs from T1. Where this result came from is by looking at this T2 line right here and literally subtracting from it the line right above for T1. So if I have this intercept 1 minus intercept 1, that term drops. I have a 0 for D1 minus a 1, so 0 minus 1 creates the minus 1 that's here. I have D2 coded 1 minus D2 coded 0. That gives me a D2 equals 1 because 1 minus 0 equals 1. And the D3 terms are both 0 and they drop. Likewise, if I wanted to have T3, I would take this line for T3, which is how that group gets its mean, minus how the T1 group gets its mean. The intercepts drop. This is 0 minus 1 to create a minus 1. This is 0 versus 0 to get a 0 here, and then 1 minus 0 gives me the 1. And so it works out that more generally, the slope that corresponds to the effect of the reference group gets a minus 1. The slope that corresponds to the effect of the alternative group gets a 1. And then whichever group is not involved, their slopes get zeroed out. The same exact process can be done in Stata with the regress command and lincoms. And here the idea that you're multiplying values of the predictor times the beta fixed effect is made explicit. So you're multiplying values times the beta and then adding them together to create the linear combination. So the first 4 lincoms give us the mean for each group, and the remaining 6 lincoms give us the pairwise comparisons, where the first 3 are given directly by the model fixed effects, and the second set of 3 are linear combinations, again with the minus 1 for the reference, 1 for the alternative, and zeros for the groups that are not involved. So to generalize this into interaction terms then, let's do a brief review. Previously, in example 6 and lecture 6, we examined interactions involving predictors whose effects could be characterized by only one fixed slope. So predictors that are binary, or predictors that are quantitative and are characterized just by a linear slope. And in that context, we added a single fixed slope to form an interaction term between those two predictors. And the role of that two-way interaction term is to take each of its constituent predictor main effects and to make them either more or less positive or more or less negative. There's only 4 kinds of interaction terms in the world, folks. It's got to be one of those 4. And we learned that the term main effect no longer applies because each of the main effects becomes simple main effects or simple slopes that are interpreted as specifically when any variables that it interacts with are 0. So as an example, if I have a model that looks like this, I have a fixed intercept beta 0, I have a covariate or a predictor, whatever you want to call it, W. W is not included in any interaction terms. Therefore, I would say that its effect is marginal. It is unconditional. Beta 1 describes the effect of W no matter what your value of these other variables are. The effect of W is controlled for the effects of X and Z in their interaction, but the effect of W that's given by beta 1 is for everyone. So these are all unique effects controlling for the other predictors in the model, but beta 1 is a marginal effect. In contrast, because X shows up here connected to beta 2 and X shows up here connected to beta 4, this main effect of X here is not marginal. It is conditional, or what people would call a simple main effect of X, or a conditional main effect. Simple slope is another term. And it is interpreted as the effect of X specifically when the interacting moderator equals 0. So beta 2 gives us the effect of X specifically when Z equals 0. Likewise, and for the same reasons, beta 3 is the effect of Z conditionally specifically when X as its moderator equals 0. And the role of the interaction term, beta 4 in this case, is to talk about how the slope for the effect of X changes as a function of Z, or how the slope for the effect of Z changes as a function of X. And notably in this example, the effect of X and the effect of Z are each characterized using only one slope. So this would be the case if they were quantitative predictors who had linear slopes only, or if they were binary predictors and it was just 0 versus 1. So we only need one interaction term to describe how each predictor moderates the effect of the other because each simple slope only takes one. But what would happen if, say, the effect of X required 2 slopes? Or the effect of Z required 2 slopes, or both? Then we'd have 2 or more interaction terms. So let's take a look at what that might look like. Here's an example model that extends our previous 4-group example. So we have control, treatment 1, 2, 3 is given by these dummy codes as described earlier, but now I'm adding in another predictor for the linear effect of age. And in this case, we're talking about older adults, and so age is going to be centered at 85. And I'm adding in interactions between age and group. So what this model is testing conceptually is whether or not there is a different effective age within each of these groups, and simultaneously, whether or not the extent to which one group differs from another depends on age. So whether the group differences vary by age, or whether the age slopes differ between groups. That is what beta 5, beta 6, and beta 7 are working together to tell us. So because I had 3 slopes to characterize the differences between my 4 groups, I also need 3 interaction terms to characterize how those group differences differ as a function of age. So the model that is right here would be implemented in SAS like this, where I have the main effects of each of these predictors by listing them as themselves, and then the interaction terms are created on the fly with the use of the asterisk. So in this case, I have 2 contrasts written out here. I would end up with an f-test provided automatically for everything that's in the model, but I want to drill down more specifically to look at the contributions of each predictor conceptually. So I could ask for a joint test of D1, D2, and D3, which would give me the overall effective group. These 3 terms work together to describe the differences between my 4 groups. But because of the model, these would be conditional for somebody who is 85. Likewise, I could create a contrast f-test for the effects of the interaction terms lumped together. So in these statements, the commas are used to delineate degrees of freedom for the numerator. They're used to say that, no, I want 3 slopes tested simultaneously. I don't want you to add them together or anything. And so this is the omnibus overall interaction because these 3 terms work together to describe how the differences between the 4 groups vary by age, or how the age slope differs between groups. So there's 4 possible age slopes that are implied by this model. And so that's what the next 4 lines are actually asking for. Okay, what does the model say the effective age is in each group? Because if I go up to this equation here, this beta 4 is conditional. It is a simple main effective age specifically when all of these interactions are 0, which only happens if we're talking about the control group. So to be able to ascertain how the model tells us what the effective age would be in any of the other groups, the rule is we go into the equation, we find all the terms that have the slope of interest, so age by itself and the interactions, we factor out age, and then the model tells us what's left. So down here, for instance, when we have age slope for control, age refers to beta 4. I need one of those at a minimum. D1 times age refers to what beta 5 is going to be, and the value that goes after it is the value for the moderator, because age is the slope we're interested in. So 0 would be what I have to fill in for D1 if I'm talking about the control group. Likewise, I would fill in 0 for D2 and 0 for D3 because that is the coding scheme that I used for the control group. So the age slope that's given by this first line is redundant with beta 4 because that's all I've asked for. The other 3 are age slopes that are implied by the model but not given directly by the model. They are given indirectly as linear combinations. So if I want the age slope for the treatment 1 group, at a minimum, I need beta 4 here to get the age slope. So that's age 1. And you'll note that that is in place in all 4 of these lines to get all 4 of the possible age slopes. Then if I look at the pattern of 1s afterward, the interaction term to which that distinguishes treatment 1 from control gets turned on if I want the slope for that alternative group. So a 1 here, a 1 here, and a 1 here. So to figure out what the age slope would be for these alternative groups, I need to add beta 4 to either beta 5 or to beta 6 or beta 4 to beta 7. That's what these 4 statements are doing for me. They are creating linear combinations of the simple main effective age plus the interaction term that is relevant in distinguishing which group I want the age slope for. So what the interaction terms do is tell us the group differences specifically. Beta 5 tells us how the age slope differs in group treatment 1 relative to what it would be in control. Beta 6 tells us how the age slope differs in treatment 2 relative to control. And beta 7 tells us how the age slope differs in treatment 3 relative to control. So the interaction terms tell us about the group differences in the age slope, but they only tell us about the group differences relative to control. However, as you may have guessed, we can get group differences for the other non-reference groups as well. So the first 3 lines in the second section here simply repeat the interaction terms, but I'm doing this for pedagogical purposes to show how you would build the other ones. So D1 times age directly tells us whether the treatment 1 age slope differs from the control age slope, and the same is true for these other 3. If I want the age slope differences between the non-reference groups, then I set the interaction term that pertains to the reference part, so T1 in this case versus T2 is the alternative, and the interaction slope that goes with the alternative is set to 1, and the other interaction is set to 0 because it's talking about T3, which is not relevant here. Similarly, T1 interaction slope for age goes to -1 here. T2 is not relevant, and T3 goes to 1. And then here's 2 versus 3. So this information would be enough to tell us what is the effective age in each group, that's given by the first part, and then how does the effective age differ across groups. And so there are 6 differences in the age slope that are implied by this model. If I wanted to talk about the results from the opposite perspective, if I wanted to talk about how group differences varied as a function of age, then I would have to do this same process, but referring to group as the effect of interest, and then age would be the moderator. I'll show you how to do that more efficiently with the other way of doing this coding scheme. So this process, here's the stated version of it. The idea of building these dummy codes and then entering them into the model as an interaction with age, the code, the equation, and the variables all converge. That's why I like starting with this, because the linear model representation of what you're asking for is very explicit as part of this process. Here is the other way of going about the same process of including either main effects and/or interactions with categorical predictors, but letting the program do the heavy lifting for you. You can tell the program to do the dummy coding by treating it as categorical. So this is the use of the by option in SPSS, the class statement in SAS, or I dot in Stata, as opposed to C dot in Stata. Most programs have the capacity to do this. M+ is a notable exception. So what would be happening behind the scenes is that if I tell the program, hey, my group is categorical. So the variable is called group. It has C equals 4 categories. It would create internally 4 new variables that would look like this. So I have named these variables according to what they represent, but these are not variables in your data set. They are internal programming variables that it's creating for you. And it creates dummy codes that gives a 1 to each group in turn and zeros otherwise. So it's more like an ID system than a set of group contrasts. So it figures out then, based on the context of your model, how many of these internally created contrast variables are needed to fully differentiate all your groups. So if you start with an intercept, which would be a column of 1s, then it doesn't need all 4 of these. One of them would be redundant, because if you have an intercept, you have one of the group means, and then you only need to get the 3 other possible differences. So it has to decide which column to leave out, and that's what creates the definition of the intercept. So in SAS and in SPSS, it leaves the last one out. So if you leave this out, then you're left with a coding scheme where you have the 3 types of dummy codes that we made manually before. So the pattern is exactly the same. Treat 3 would be the reference, because that's when all 3 of these variables are 0 if this one is missing. Alternatively, if it left the first one out, which is what Stata does by default, then it would use these 3 variables. The control would be the reference, because that's when they are zeroed out, and the rest of this looks exactly like the D1, D2, D3 dummy codes we created. So the nice part about it is that it builds these internal variables for you. The hard part is that then every time that you refer to group in the model syntax, you need to tell it what value you want each of these internal variables to represent. So in SAS and SPSS, the last group is the reference by default. If you want to change that, I would recode the variable, because even though you can change it in the syntax, it doesn't do so in an internally consistent way, and I've found that to be a bigger headache than what it's worth. In Stata, you actually have the option to change the reference group. The beginning group is the reference by default. In several of my examples, you'll see this code. I change it to the last so that the results from Stata map directly onto the results from SAS or SPSS. And I'll show you the additional pieces of syntax that you can use to ask it to give you model predicted means per group as well as simple slopes per group. And I note that, by the way, none of this applies to M+ software, at least in its current version, which is 8.5, I think. So this is what it would look like to denote the original group predictor as categorical. It happens with this little line right here in SAS. Welcome to the class statement. Class stands for classification variable. So by putting group on this statement, you are saying, hey, can you make dummy codes for me? As many as you need to differentiate all the groups. Okay, thanks, bye. And then you can put group into the model, and it understands that when you represent group as one word, you're representing all the dummy codes that are needed to differentiate all of the groups from each other. And so the use of the class statement also allows you to specify this statement, which is ls means, stands for least squares means. And putting group on here means, hey, can you give me what the model says the mean should be for each of my groups? Oh, and by the way, diff equals all allows you to get all possible pairwise differences. So class group and ls means group diff equals all, those two things give you all this stuff. So all 10 of these estimate statements, as well as this contrast that lumps the three codes together, are all given to you by the use of the class statement. I have written out how you would ask for that information in this new way of designating the group variable. So you'll note that in these statements below, everywhere that you see the word group, you have to fill in the patterns of zeros and ones that denote for which group you're either asking for the mean or the mean difference. So if the intercept is in the model, to get the mean for the control group, you would put a 1 here that corresponds to this table right here that is creating internally. So you would turn on the internal programming variable that corresponds to that group's identification. So control 1, 2, and 3 here. Otherwise, it doesn't know for which group you're trying to get some kind of prediction, and it won't work. So then under this way of representing how each group gets its own mean, the intercept plus the difference, the intercept plus then these internal variables, it then computes the differences. And so then to get group differences explicitly, get tests for those, it would be this part of it, the intercept drops, where for instance 1 minus control, that would give you 0 minus 1 is the minus 1 here, 1 minus 0 gives you the 1 here, and the last set of zeros drop out. Similarly, if I wanted to do, say, T3 and T2, so T2 is the reference versus T3, then I would end up with zeros and zeros in the first two places. And looking at this here, I need, the last two. Sorry, I'm off one column. 0 minus 1 gives me this minus 1, and 1 minus 0 gives me this 1. So again, you don't have to write any of these 10 statements. ls means group diff equals all gives them all to you. But if you needed to, here's how you would do that. And you would need to in the context of interactions and getting simple slopes per group or simple slope differences. Likewise, to be able to write out a contrast, this is given to you by default once SAS understands that you're going to want an omnibus effective group that lumps all of these contrasts together, but this is what it would look like to ask for them. So it's 3 contrasts, 3 sets of pairwise differences is all you need. It doesn't matter which 3 so long as they're not redundant. And then I'm also demonstrating down here how you would tell it to lump things together across groups. So for instance, if you wanted to build a combined mean that collapses across the three types of treatments and just talk about a treatment group mean, you could do that by putting the control at 0, setting ones to the three treatment group means, and then this divisor option means divide by 3. So that way it would be like a third, a third, a third. Likewise, if you wanted to then contrast the difference of control versus the mean of the treatment groups, if each of them is a third, then the opposite of that would have to become -3. So the sum of these things has to be 0 for it to represent a difference, and that is true in each of these contrasts given here as well. In Stata, the same ideas look a little bit different. So here's a use of I dot for group, and so I have I and then changing the baseline to be last. I'm doing that simply so that the results that you would get from the SAS specification would match those of Stata, but you can pick whatever reference group you feel like. Contrast is something that you do have to add. It's not provided by default. Contrast I dot group gives you the omnibus group test. So all the pairwise, all lumping all the individual contrast variables together, 3 in this case, is what contrast gives you the F test that corresponds to that. So that would be the same thing that's automatically provided in SAS. You do have to ask for in Stata. And then margins. I dot group gives you margins, would give you the group means, and then an option PW compare, which stands for pairwise comparisons, would give you the group differences. The margins line up above gives you all 10 of these lincoms, but in case you needed to ask for something more specifically, I wanted to show you how you would use the syntax in this I dot group fashion. So the group means are all functions of the intercept, plus you would have to turn on each of the group contrasts. So in the same way that you have variable 1, 2, 3, 4 in SAS, which goes back to this table right here conceptually, this would be variable 1, 2, 3, 4 in Stata is made explicit. 1 dot group means that first column. If it's the control group, turn it on. 2 dot group is the next column, 3 dot group, 4 dot group. So you're referring to the internal contrast variables with the number dot in front of the grouping variable that it understands is categorical because you made this I dot specification for it in the regress command, or in the mix command, as it were. And so then the same pattern of zeros if it's not relevant, -1 and 1 if you want the differences where -1 is the reference and 1 is the alternative, and 0 if it's not relevant for all of the others. And as far as I could tell, there is no divisor option for lincom, so I tried to do the same thing here with the 33 and a third, where one of the groups had to become 0.34 so that the whole thing would sum to 1. So a little clunky, but it works for the sake of an example. So when would you need to go to the trouble to write out these lincoms if margins would do it for you? And similarly, if you can get all of this group means and group mean differences in LS means, when would you need to go to the trouble to write these estimates out? When you have interaction terms. So let me show you the categorical version of the same model that we looked at before. So just to recall this idea, where we have differences between the 4 groups and how the age slope differs between the 4 groups. This is what it looks like if I'm doing the manual coding. So this is what it looks like in SAS on slide 8. This is what it looks like in Stata on slide 9. Here's how I would do it if I let the program do the heavy lifting. So the class statement in SAS tells it that I want dummy codes, contrast variables built. So 4 variables will be built because I have 4 groups. So group goes in the model statement, age goes in, and group by age. So the 3 dummy codes that we had before are replaced by group. The 3 interactions of the dummy codes with age are replaced by this single interaction term. So this single interaction term is actually referring to 3 fixed effects simultaneously. Likewise, this simple main effective group is referring to 3 fixed effects simultaneously. So this is why I don't teach this to start with. It does not correspond to the actual model. It's a shorthand. Once you understand how this stuff works, the shorthand makes it convenient, but it does not help you understand what's going on until you can do it yourself. So, for those of you who are wondering why I made you go to all of the trouble to code things, it's because I strongly believe I want you to know what SAS and Stata are doing under the hood for you when you invoke these shorthand conventions. So I have code here then to ask for group means at specific values of age as the moderator. So if I wanted to talk about group mean differences and how they change as a function of age, this set of commands would help me do so. So ls means group is going to ask for what's known as adjusted group means. So they're the means holding any other variable in the model constant at some variable. So I'm holding them constant, say at age equals 80, because age is centered at 85 in this example. And we have difference equals all, gives us all possible pairwise group differences. So six differences at age 80, 6 differences at age 85, and 6 differences at age 90. And I could ask for these for any ages that I wanted, but this would just be a way to sort of illustrate what's going on. I could use this information to make a plot, for instance, to show how group differences change as a function of age. If I wanted to go the other route, I could then talk about the effective age and use group as a moderator. So this is how I would ask for the age slope within each group. At a minimum, I need to start with what the age slope is. I would then need to tell it for which group do I want the age slope, where 1 means turn it on for this group and 0 means not relevant. That coding scheme then of the 1s and 0s, I could then use to get group differences in the age slope down here. So because age 1 is common to all of these, it drops. And then I'm left with the differences between these lines as how each of these age slope group differences would be found. So for instance, control versus treatment 1. If I have treatment 1, the second line here minus the first, 0 minus 1 gives me the minus 1 here. 1 minus 0 gives me the positive 1, and then the zeros in their other two places. So more generally, the group that you want as the reference for the comparison is the minus 1. The group that you want as the alternative is the 1, and zeros are used for the groups that are irrelevant, and these must sum to 0 within a line. And here's the same idea with the divisor option, so that you could lump together age slopes across groups and test age slope differences across groups as well. Here is the same thing in Stata, where I dot and then the number is used to denote the group. It looks like I have something that's inconsistent here. Yeah, I think you can just type the number or I dot the number. I could be wrong about that, but this is I pulled this from a couple different places. So if it yells at you when you have the I dot, take it off, and if it yells at you without it, put it back on. So I dot. C dot, by the way, is for quantitative variables. So it needs to be either C dot or I dot in order to use these things in a lincomp so that it understands what to do with this information. So the age slope for each group, so a 1 used for whichever of the internal contrasts is active, the others are implicitly zeroed out by not writing them. And the same is true down here. I did not write out the other groups that were irrelevant to each comparison to save space. And this would be the linear combinations across groups that were demonstrated but without divisor in Stata. So this approach of telling it I dot in Stata or telling it class, it can allow you to get more information quickly, such as group differences or adjusted group differences holding variables of the covariate constant, but it also complicates the interpretation of what the interacting variable means. So in this case, here are 3 different renditions of what it would mean to have this, what is actually the same model but specified differently. So let's say that I had gender as a binary predictor, so 0, 1, and I've got my group here. So in each case, I'm saying that group is categorical. I'm going to let SAS or Stata do that coding for me so it creates those 4 internal contrast variables. And the question is, what happens if I also tell it that gender is categorical, because technically it is, it's 0 and 1, or if I treat it as a quantitative variable, which I'm also allowed to do because it's a 1 unit difference, takes me from the 0 group to the 1 group. So in testing, the main effect of sex that's going to show up on my output and what's known as the type 3 tests, I'm doing air quotes as if you can see me, that's what would be given from the contrast statement. It's given by default when you invoke um, the solution. It's not something I typically show unless it's necessary for multiple degree of freedom tests. But the test for this is going to be if sex is denoted as quantitative, this is going to give you the marginal difference across groups. The group main effect, though, is going to be conditional on gender equals 0 because it's being treated as a covariate. So the main effect of sex, it understands that it needs to marginalize across groups. The group main effect is going to condition on sex if it's treated as a quantitative variable, but it's going to marginalize across it instead if it's treated as a categorical variable. So what looks like the same test will actually give you two different pieces of information depending on how sex is treated, whether it's treated as quantitative if you just leave it off the class statement or put it as C dot versus treated as categorical by adding it to the class statement or adding it to I dot. The interaction term is the same either way. So what this boils down to, and what we'll see in the example that goes with this lecture, is that you can get two different p-values in your output that supposedly both refer to what the main effective group is, and they mean different things because it depends on whether the program is marginalizing across the interacting variable or whether it's conditioning on it. So we will see that, and it's potentially very confusing. So in traditional presentations of analysis of variance, so if I have one categorical variable interacting across another, so two-way analysis of variance, three-way analysis of variance, and such, the traditional version of that model, by default, includes all interaction terms, all highest order interaction terms. So when you specify that, say in the fixed factors box in SPSS, which is where I first learned to do this, it puts in all possible interaction terms, and you would typically interpret your results without changing that, even if the highest order interaction terms were non-significant, which to me is crazy, and it's very different from a linear model's perspective where you would only keep the things that are necessary either because they're lower order or because they're significant. So the default ANOVA output when you have interactions among categorical predictors are to make all of the main effects marginal. So it would average, marginalize across the other variable in giving you the main effect of each predictor. So it's not for any specific group, it would be on average, which is basically useless when it comes to interpreting interactions. Likewise, if you have more than two groups for either of the interacting categorical predictors, then it gives you an omnibus f-test that marginalizes across the different interaction contrasts to give you the interaction overall multiple degree of freedom test. And while that might be something to report, it doesn't actually help you interpret the interaction. It doesn't tell you where the sources of the differences are. So it's useful to decompose that multiple degree of freedom interaction into specific single degree of freedom contrasts. And so I want to show you how to get all of that additional information when you have interactions among categorical predictors that would actually allow you to figure out what the hell is going on. So that is the logic behind example 7. Just as a note, the same principle, the idea that you need more than one interaction term anytime that your predictors to be interacted are characterized by more than one fixed slope. Here's another example of what that might look like in the context of quantitative variables that are characterized by more than one slope. So in 6242, we had an example using the GSS, General Social Survey data, in example 4 and lecture 4, where we were looking at the effect of education. And education I had divided into 3 regions and fit what's known as a piecewise linear model or a spline model, where different slopes are estimated for different regions of education. So I had one slope that described the effect of education amongst people who hadn't graduated high school, another slope that described the shift as a function of graduating, so it's a binary predictor, and a third slope that described the effect of education among those who had graduated from high school or more. So education is represented by all 3 of these slopes. So that would mean that if I wanted to test, say, whether the effect of education was moderated by gender, men versus women in this example here, I would need to have all 3 interaction terms. So I would have to lump together beta 6, beta 5, beta 6, and beta 7 to get an omnibus test of the interaction, but that wouldn't tell me exactly what's going on. Similarly, I would have to lump together beta 1, beta 2, and beta 3. That would describe the overall effect of education, but it would be specifically for men equals 0. And I could compute simple slopes for what the effect of education would be for women in the 1 group, which would be linear combinations of beta 1 plus how it differs for women in beta 5, beta 2 plus beta 6 for those who graduated high school, and then beta 4 plus beta 7 for the effect of education in women among those who had more than high school. So this gets tricky real quick, and I note that if I were to modernize my conceptualization of gender and allow it to be something non-binary, meaning more than just men versus women, if gender itself required, say, 2 predictors to differentiate amongst 3 groups, then that would add yet another 3 interaction terms. So there would be 6 different terms in the model that would convey how the effect of education varied as a function of gender. So this stuff can get complex real quick, but the nuts and bolts of it all work the same way, no matter how many interaction terms. Each provides you with a difference between one group versus the other, or it provides you with the difference in a slope for one group versus the other, and you can work across the equation to figure out how the model tells you what the slope or a slope difference or group difference would be for any combination of the moderating variables. So that's where I'm going to leave off. The next video we'll examine example 7 to demonstrate how to ask for more useful information when you have an interaction amongst 2 categorical predictors. Example 7 also follows exactly section 3 of chapter 2 of my book. So stay tuned for that. Thanks for joining me. Stay well, stay safe.